Okay, the next two examples are examples of where we would use the compounded continuously formula. So in this first example, it says, suppose an investment account is opened with an initial deposit of $13,000. It earns 8.2% interest. How much would the account be after 30 years? Now, here are the keywords you're looking for so that you can determine the difference between compounded a certain number of times a year versus compounded continuously, so you know which two of those equations to use. This one says it's compounded continuously, which means we're going to use this formula instead of the formula that we used in the previous couple of examples. Okay, so all we have to do is find all the information and plug it into the formula. It says we initially deposit $13,000, so that's our value of P, our initial value. If we were to look at it on a graph, it would be our y-intercept. That's our principal, times E. Our rate is 8.2%, and whenever we put that rate into our formula, we want to make sure we put it in as a decimal, so 0.082. And we want to do this for 30 years. So that's what's going to go in for the T. Okay, so when I put this in on my calculator, I'm going to put in 13,000. Then I'm going to choose that E button that's next to the 4 on my calculator. There is a button that says ln for natural logarithm. And then right above that, it says e to the x. So you want to choose that e to the x button by choosing the second option. And so it's going to pop up and it's going to look like this. And then you can fill in the parentheses, e to the power of 0.082 times 30. You may have to close the parentheses. Depending on what model you have, it might automatically insert both parentheses, or it might just do one, or you might have to put them in. Okay, when you hit enter, you are going to get 152162.55. So $152,162.55. Now for the second example, this one talks about animal population. And a lot of times we can use that natural exponential function to model the population of animals. And in this problem, it says the growth rate is 9%. So that's what we're going to put in for R. But we're going to put it into the decimal, so make sure you remember to put in R as 0.09 and not 9. And it says we're starting to track this in the year 2012. This is when we're starting. So my starting population would be 20,000 or 21,600 foxes. It's asking us to find the fox population predicted in the year 2019. Okay, so here's a common mistake that I want to point out. When I put in my P, which is my starting value, that's the starting value population for the foxes. So that's going to be the 21,600. Then I put in my E, and my R and the exponent is 0.09. But here's where a lot of people make a mistake. I'm not going to put in year 2019 for T. T, the amount of time is the amount of time that has passed. So from 2012 to 2019, that is 7 years that has passed. So I'm going to plug in T is 7. So be careful not to make that mistake and plug in 2019. You want to plug in the amount of time that has passed. So you're going to put in 7. When you do that and you put that in on your calculator, you're going to get 40,556 foxes, 0.39. Now, we don't want a partial fox, so we're going to round to the nearest fox, and we would put our answer is 40,556.